Hello, everyone. Good morning. Welcome. Thank you for joining us today. My name is Dani Akish. I'm the marketing manager at Intercad and AXISVM. And today's topic will be about the soil structure interactions. Today, the session will be led by my colleague Zsófia Kapui, who is an expert on the topic. And the presentation itself is scheduled or was scheduled to be about 30 minutes. It might be that we are doing it a little bit longer, but hopefully you won't mind. Just some administration information. The session will be recorded and it will be shared after the event itself. Please use the chat to ask any questions. If we have some time, then we'll do our best to answer them at the end of the session and the presentation. And if not, then our colleagues from the support team will connect you via email and answer your questions, which we didn't have the time to answer still in the upcoming 1-2 days. And I think that's all from my side, and I will pass on the microphone to my colleague Zsófia. Thank you so much.
And good morning, everyone, and thank you for joining this webinar today. My name is Zsófia Kapui, and today I would like to talk about the soil structure interaction and how soil module can help us in common engineering situations. When we discuss soil structure interaction, we often focus on settlements. However, it's not just about settlements. The subsoil influences how the structure behaves and how load transfer is existing in the structure itself, and how the structure responds to the variable soil conditions. These effects are often underestimated. However, this effect can be significant. In this webinar, I would like to show how soil module can help to analyze this effect. Now let's dive into the topic. At this point, maybe the question is, what does soil structure interaction mean? And to tell you the truth, I think it's a very good question. And actually, it means that soil and structure do not behave independently, but behave as a coupled system. The soil deforms under the applied loads, and the structure with its stiffness tries to resist this deformation. This interaction leads to load redistribution within the structure. The significance of this effect depends on several factors, such as varying soil conditions, or whether the structure is self-sensitive to settlements. In many cases, relative settlements are more important and have a significant effect than the magnitude of the settlement itself. And now let's see how AXISVM SOIL Module can help us. And SOIL Module provides three main capabilities. The first one is Winkler-by-soil-profile, where the support stiffnesses is derived in every single point based on the borehole data and the generated soil profile. The second one is the 3D continuum model. In this model, the solid is modeled by using 3D finite elements. And the third capability is the initial stress state. It helps us to take into account preloaded conditions. In the following part, I would like to demonstrate the practical relevance of SOIL module in common engineering situations. Support stiffness determination is often treated as a small modeling detail. However, even a simple support condition requires several engineering decisions. For example, how to determine vertical, horizontal, and rotational stiffness, or can soil and structure be handled separately? Each of these assumptions affect the behavior of the structural system. And now let us start with the determination of vertical stiffness. At first sight, it seems straightforward, but it depends on several factors, such as, just a minute, such as the subsoil under the foundation, or the footing foundation, the dimension of the foundation, the estimated load, and the method we have chosen. As a result, there is often no single correct value. Engineers must make decisions and simplification on the available informations. Another important aspect is that the support stiffness depends on the load level. But what does it mean? This means that loads are transferred to the ground, and under the foundation, this causes stresses. This way, the loads influence the support stiffness, which in turn influence the structural behavior and the response of the structure. This creates an interaction loop between soil and the structure. Finding the appropriate stiffness is often requires several iteration steps. And this example also illustrates that soil and structure can't always be handled separately. The uncertainty is present during the determination of horizontal and rotational stiffness too. How should we calculate the horizontal stiffness based on friction or shear modulus? And how should we calculate the rotational stiffness? It depends on the geometry and stiffness of the foundation and the rising stiffness below it and the soil parameters. Different assumptions may lead to different results. In contrast, in a 3D continuum model, the structure and the soil are analyzed together as a coupled system. In this case, no need to calculate spring stiffnesses, but the results from the behavior of soil and the foundation. The stiffness emerges from the system behavior. This allows soil structure interaction to be considered in the analysis. Another interesting aspect is the information about the available information about the subsoil. In practice, we often have limited information about it. We know the soil just in a few points of the under our building. So we know the borehole data, and we have to interpolate the soil layers between these boreholes. So the challenge is not only analyzing the soil, but deciding how to take it into account in our design process. There are several modeling strategies to take it into account. One option is to use an average stiffness over the entire area. Another strategy is grouping the whole area into zones based on the subsoil and to calculate the stiffnesses for each zone. Another strategy, which is a more conservative one, is the worst-case assumption. The importance of these decisions became more significant if the subsoil is highly layered or in presence of a local weaker soil inclusion. It is also not so easy to determine how far the influence of a local weaker zone extends. And I know I repeat myself, but different modeling assumptions may lead to different structural response. To better approximate the soil condition, the Winkler-by-soil-profile can be a good choice. It derives support stiffnesses based on the foundation and in every single point based on the generated subsoil profile. This way, layered or varying soil condition can be better approximated. On this slide, you can see two models. On this model, the support stiffnesses are derived from one single borehole, while in the other, the support stiffnesses are determined based on the soil profile. The characteristic of the deformation is similar, but there are differences between the two models. If we have a look at on this column, we see that the deformation or the settlement is greater than in the other model. This this effect can be seen on the deformation shape of the slab also. In this way, the settlement difference influences not only the deflection, but the reinforcement of the slab or the punching reinforcement or some other design results. It can be also stated that, that the soil profile can approximate the variability of soil better. And it is also a good tool to determine the governing mechanism of the structure and the soil system. And it can be also a good choice between a more complex and the Winkler solution, because it approximates the variation better, but it still it is better from computational side. Let's say some word about the limitation of Winkler method. Despite the practical advantages, it still have some limitation. The springs behave independent systems. The deformation of spring does not affect the adjacent springs, as it is shown by the red line. As a consequence, shear transfer or shear transfer within the soil is neglected. The soil behaves as a collection of independent springs rather than the continuous medium. As Pasternak and modified Winkler methods are closer to a continuum behavior, but support interaction is still limited compared to a 3D model. This simplification is often acceptable, but its limitations has to be always taken in mind. Have to keep in mind. In reality, the soil behaves as a continuous material. Settlements zone generated by the nearby foundation can affect on each other. This situation, not just the settlement zone, but this way the whole deformation of the building itself. This situation can occur in case, for example, at expansion joints, very close columns, nearby buildings, neighboring buildings, industrial buildings, and heavily loaded cores. The structure itself may be separated while the soil remains a continuous system. This continuity creates interaction. And in certain cases, this interaction cannot be handled by using independent springs. One of the consequences of this interaction is the load redistribution. As the deformation of the structure changes, the load transfer is also changed within the building. The internal forces are redistributed between the columns, walls, and foundation. And this is the most important. Reason why soil interaction is not just about settlement. And the structural consequences sometimes can be more significant than the settlement itself. Now let's move on the initial state of soil. Existing building and structure, and also the soil, the self-weight of the soil, occur stress and deformation already in the soil. But this deformation has already happened. The soil module helps us to take into consideration these initial stresses, and it also ensures that the previous deformation do not affect the further deformations of the building. This is particularly useful when analyzing preloaded systems and neighboring structures. Now, let's see when soil structure interaction became relevant. And the answer is that soil structure interactions became relevant when the deformation of soil started to influence the deformation of the building. Typical examples are closely spaced foundations, settlement-sensitive structures, layered or variable soils, weaker soil inclusions, large mud foundations, heavily loaded cores and walls, neighboring structures, and preloaded subsoil conditions. Before moving to the case study, I would like to briefly discuss some practical modeling issues. It is important to note that in a 3D model, the foundation have to be modeled with their own dimensions. There is no need to replace the foundation with supports and equivalent springs. This helps to avoid unrealistic settlement pattern and stress concentrations. Another important question is how to determine the size of the domain. The size of the domain have to be larger than the structure itself. And it's an important rule that the further size increase should not significantly affect the results. But what does it mean in practice? A good rule of thumb is to choose the vertical dimension twice as big as the width of the structure itself, and the horizontal dimension 3 times as big as the width of the structure itself. Finally, a few modeling assumptions should be kept in mind. The soil module uses a linear material model for the soil. And this is why some geometry geometrical rules have to be followed. Such rules that the slope angle is limited in 35 degrees, or vertical cuts and jumps are not allowed in our model. And another important rule that the structure must remain on the surface of the soil model. This is why basement and the excavation cannot be modeled in soil module. So far, we have discussed the theoretical background and the practical challenges associated with soil model. We have seen that small details can have significant effect on the structural behavior. Now I would like to demonstrate this effect in a practical example. And now let me switch to the AXISVM program. So here we can see the structure. Here we can see the investigated structure. It is a relatively simple reinforced concrete building with mat foundation. It is symmetrical, and just a second, and have a center core, and slabs are connected by columns. The base plane of the building is 36 by 36 meters, while the height of the building is around 26 meters. Maybe I mentioned it already that the building is symmetric itself. I would like to show that I have applied only vertical loads and only uniformly distributed loads in order to take into account the effect of the soil variability. Here we can also see the soil model itself. The dimension of the model is 96 by 96 meters, and the height of the model is around 30 meters. Although the building itself is relatively simple, it allows us to investigate the subsoil variability, not the complexity of the superstructure. We can see that the soil model is a layered model, not so extremely, but we can see here with pink a weaker soil inclusion. We will investigate the effect of this inclusion. And let's see the results, the final result. Now we can see the deformed shape of the building. Maybe a section can represent the deformation shape better. And we can see then the deformation shape is very similar to the expected one, because we can see the settlement basin and the tilt of the building is noticeable. This is because of the soil, the weaker soil inclusion. Now let's switch back to the slides. Here we can see again the investigated building, the geometry of the building. And let me stop for a moment here at this slide, because I would like to show again the layers of the soil. I have applied 2 sandy soil. These are stiffer layers, and I have applied two clay layers, which are softer layers. I have applied a weaker soil inclusion. It is represented by this KK4 clay layer. Here you can see again that is not an extremely layered soil, and I intentionally decided next to it because I wanted to demonstrate that a slight effect has also important role in the formation of the building. Now, let us first compare the deformation shape of the different modeling approaches. This model on the left side, it was made by using average Winkler stiffnesses. The middle one was built by interpolated Winkler springs. And the third one is the 3D soil continuum model. If you have a look at on the deformation shapes, we can see that the deformation shape of the Winkler model is follows a slight and smooth settlement basin, while the deformation on the edges are not similar as we expected. In case of the interpolated Winkler model, the tilt of the building is noticeable. The third model, a 3D model, captures all the two effects in one. It shows us the tilt of the building and shows a more realistic settlement basin. But at this point, the main question is why are these deformation shapes are so different? And to answer this question, we need to understand what is happening behind these results. Let us focus first on the average Winkler model. What we see is not surprising. It is actually a well-known phenomenon. The average Winkler models assume that each support behaves as an independent spring. But in reality, loads and stresses are spread through the soil and the surroundings, and also in the surrounding soil. As a result, the response of the region influences the neighboring regions too. This interaction cannot be fully represented by independent spring. To particularly account for this behavior, I have modified the model and applied increased Winkler stiffness around the edges of the building and average stiffness in the middle part of the building. As a result, the deformation shape became closer to the expected one, and now the 3D and the modified Winkler model show very similar deformation characteristics. It does not make that the two models are identical, but the behavior and the deformation shapes are closer to each other. And it also shows us that the soil continuity has effect on the deformation shape. Okay, let's move on to investigate the interpolated Winkler. On the first picture, on the left side, we can see the deformation shape of the interpolated Winkler. Here we can see again the weaker inclusion. The second model, in case of the second model, I have eliminated this weaker soil layer in order to affect because I think that this tilt is because of the weaker soil inclusion. That's why I have eliminated this weaker soil inclusion to check the deformation shape. Now we see more symmetric deformation shape, but also the effect of the layered subsoil system. In this case, I have again modified the interpolated Winkler model. I adjusted the soil, the stiffnesses around the edges. I increased them and used the interpolated Winkler stiffnesses in the middle. Now the result is again closer to the expected one. It contains the effect of the local weaker zone and also the increased edge stiffnesses. Yes. This example shows us how interpolated Winkler model can help identify the governing mechanism, and it also demonstrates that with an appropriate adjustment, it may provide a practical approximation of actual soil behavior while maintaining the efficiency of Winkler-based approach. Now that we understand the governing mechanism, we can compare the final modeling approaches. The modified Winkler stiffness represents the influence of soil continuity, while the interpolated Winkler stiffness can approximate better the varying soil condition. And the 3D continuum model naturally captures both effects simultaneously. The objective is not to find the best model, but to understand the strengths and the limitations of each approach. We have also seen that with a proper adjustment and calibration, simplified models can be significantly improved. And the figures on this slide do not show numerical values. This is because I would like to focus on the similarities and the differences between the deformation shapes. With this case study, I also wanted to demonstrate how to investigate which effects are dominant and how the soil module can help us find the most appropriate modeling approach for a given design situation. The next step is to investigate how the different deformation patterns affect the structure itself. For this comparison, the modified Winkler approach and the 3D model was used. It was an intentional decision because I wanted to show you what happens if we neglect the effect of a weaker soil inclusion. And at this point, I would like to refer back to the loading and the geometry of the building. As I mentioned it earlier, the structure is symmetric and the loading is also symmetric and contains only uniformly distributed loads. Therefore, asymmetric effects arise only from the subsoil. This slide compares the bending moment of the columns from the under self-weight. The effect of the different deformation pattern becomes visible in the structural result. Let's see this modified Winkler model. If we have a look at on these columns, and these columns, and compare the distribution of moments, we can see that negative moments and positive moments are very similar. the distribution of bending moment is symmetric. And when we see the results of the 3D model and make the same comparison, for example, we have a look at on this column sequence and this column sequence, we can see that the moment distribution is not symmetric because the negative moments are different and also the positive moments are different. And we can also see that the moment has increased in the case of the 3D model. Let's summarize it. The moment distribution has changed. In the modified Winkler model, the moment diagram is almost symmetric, while in the soil model, the effect of tilt appears in the column moment. Bending moment distribution is not symmetric, and the moments increase in the direction of the tilt. So the inclusion, as a weaker inclusion, was here, and the tilt of the building happening around the y-axis. And we can see this bending effect in the columns. And at this point, don't forget this result only of the self-weight. The effect appears in every load case and accumulates at the end. This comparison demonstrates one of the most important effects of SSI. Changes in subsoil behavior may directly influence structural forces. Let's move on the axial forces and investigate the normal forces. For this purpose, I have created virtual beam on the cores in order to make it easy to compare the normal forces between the two models. In case of normal forces, the differences remain visible, but the magnitude of this difference is not so significant than in the case of moment diagrams. And it is an important observation because SSI does not necessarily affect every structural result. Differences arise only from deformation shapes. In this example, the tilt of the building caused by the subsoil was different. This is the reason why the bending moments have changed. The results can be analyzed further, but I think we now understand the main story. As a conclusion, let me summarize the main messages. Soil and structure behave as a coupled system, not as an independent system. The continuity of the soil medium may create interaction between adjacent foundation and influence settlement shapes and also the whole deformation shape. Changes in soil behavior may lead to load redistribution within the building or the structure. Soil variability or presence of weaker soil inclusion can have significant effect on the response of the structure. And finally, different approaches capture different physical mechanisms. The objective is therefore not to find a universally correct model, but to find the most appropriate model for the given design situation. And soil module can help us to take this decision and investigate these effects. Better understanding and modeling of the soil can lead to a more economical structures. And thank you very much for your attention.
Okay, thank you very much for the presentation. I hope everyone found some interesting things in it and you learn something valuable for your work, we received a few questions. We are almost overdue, so whoever we can't answer the questions, we'll reach out to you directly in email and answer them in a written form. But I think I can read out just a couple. First being, can the software model the uplift of a foundation slab? I can pass the microphone back to Zsófi, and I will mute myself just not to have interference.
Yes, about the uplift. So yes, soil model can take this effect into account, because if we run a nonlinear analysis, it can be taken into consideration. But the fact that because of forward loads, the structure itself can separate from the soil. So yes, we can take it into consideration.
Great, thank you. Let's go for the next one. Let's say, can the soil module calculate the initial stress state for a sloping ground? Can the model handle an unbalanced horizontal loads? Back to you. I'll mute myself.
Yes, we can model slopes in soil model, and it can the module can calculate stresses also in inclinations, but it is important to note that there are rules, as I mentioned also in the presentation. That is a linear material model, and the slope angle is limited into 45 degrees, and vertical jumps are not allowed, but the program can calculate the stresses in inclinations too. And it is, I would like to mention that as it is only a linear material model, it is not appropriate to analyze the geotechnical things in the model.
Thank you so much. Received a bunch of more questions, so I just want to reiterate that we are going to answer every one of them. But let's go for a last quick one. Does the soil module only work with shallow foundations or also with higher foundations?
So yes, it's a common question. But at this point, soil module can only work with shallow foundation. High foundation is not allowed yet because it is a linear material model, and amendment are also not allowed in the model. But we hope we can improve the module in later stages. I hope I managed to answer the questions.
Thank you so much, Zsófi. Yeah, a bunch of questions. Just quick information that you might expect some updates on the soil module even this year. The sneak peek, but that's enough information for today. Thank you again for everyone who stuck around and came, registered. Hope you had interesting things to hear, and would answer the remaining questions as I already mentioned. Thank you so much. You will receive the recording of this webinar in email later today. And in the meantime, if you have any questions, then feel free to reach out to us via email or through the website. Thank you so much again, and have a lovely day.